just Zoom recording, and this is pretty much where we left off yesterday in our discussion. We were talking about some of the activities and some of the ins and outs and definitions of electrochemistry and how you have to be careful about what's getting oxidized and what's getting reduced and which side of the reduction potential chart it's on. So you have to be careful. And of course, you have to check to make sure that you're using the reduction potential chart and not the oxidation potential. But they're both related and you get the same information from both of those. And so that's where we left off. Now this plate, let's see, it just talks about some of the things we were talking about last time, the sign of E cell and the spontaneity. We know that there's a relationship between E cell and delta G, which is the thermodynamic quantity that tells us if we can expect a process to be spontaneous as written, or if the opposite process is spontaneous. So we have to look at the sign of delta G to tell us that. Now, just to see that we're on the same page, if the sign of delta G is negative, what does that mean as far as spontaneity?
That it is spontaneous?
Yeah, that's right. It is. Thanks. So there must be a sign change in the relationship between delta G and E cell, and there is, and we'll see how delta G is defined in terms of E cell. Now, we know that a battery runs spontaneously, and we can check the voltmeter reading in a battery, and we know that it comes out positive. Now, what if we were to check a voltmeter reading on a battery that we set up in the lab and it came out negative? What does that mean? Well, that means that you probably hooked it up incorrectly. In other words, what you thought the anode was actually the cathode, and what you thought the cathode was the anode. So you hooked the red up to the negative terminal, the anode, instead of putting the black there, and the red needs to go in the positive terminal. And you'll define those in lab, and you'll see, how those definitions play out, and try to use the stuff that we talked about in lecture to help you with that. But in lab, there was one, the last part of the lab, you had to set up the silver copper cell, and you dumped in a source of chloride into the silver half cell, which caused the precipitation. So just real quick, you have your let's say copper, silver, Ag plus, salt bridge, and voltmeter. Now, when you added in chloride over here, it caused the precipitation. So much precipitation was in there that the spontaneous reduction of the silver in this setup was no longer spontaneous, and the E cell value was around a negative 0.07 volts, which signified that there's so little of the silver from this precipitation that there just wasn't enough to reduce to form the solid silver. So there wasn't enough silver ion because it all precipitated with chloride to give you that silver chloride white precipitation. So in that case, the spontaneous direction or flow of electrons switched because of the lack of availability of the silver +1 um, ion. Any questions on that? All right. This plate introduces that relationship between delta G and E cell. So we see that there is a sign change just as we expected. That's for E cell. And so when E cell is positive, we see that delta G is going to be negative because of that sign, and the process is predicted to be spontaneous. So delta G is found equal to NF. N is the number of moles of electrons transferred in the redox. F is the famous Faraday constant, named after Michael Faraday, who did a lot of work in this area. And Faraday's constant is 96,500 coulombs per mole of electrons. So if you multiply N times F, that's the charge in coulombs. And so you take a coulomb and you multiply that by a volt. So this is a coulomb here times a volt. That's a charge through a potential difference. Hey, that's energy or that's work. And that's the maximum work that you can extract from a process with a negative delta G. So we already know that delta G equals the max work. And so it's not much of a stretch to derive this equation, just like you would say that energy is a force through a distance in physics. You could say that energy in electrochemistry is a charge through a potential difference. And that gives you the maximum amount of work in joules that you can get for any spontaneous process. Any questions on that? So we're good. All right. So we use this new relationship we have here with delta G and E cell. And this just further cements the sign convention for the two, whether it's spontaneous or not. And there's other things connected with spontaneity, which we sometimes refer to as product favored. And if it's non-spontaneous, it would be reactant favored, or the opposite reaction would be spontaneous. And here's your value for Faraday's constant here. All right, so what we're doing now is uh, taking a look at E cell, and when the battery is dead or it reaches equilibrium, E cell 0, and that implies that delta G, since it equals minus NF E cell, is also 0. So that tells us that it's an equilibrium and it corresponds to that. Well, there should be a relationship between E cell and the equilibrium constant, and we'll see that that's true coming up in a little bit, because if there's a relationship between E cell and delta G, and there's a relationship between delta G and the equilibrium constant, then of course there's going to be a relationship between E cell and the equilibrium constant. But anyway, real quickly, we can take a look at the Nernst equation, which you're going to use in the lab in order to calculate concentrations. So you can use the Nernst equation to help calculate concentrations experimentally. And you can also use the Nernst equation for what's called concentration cells. And we'll take a look at that in just a second. But as far as the lab goes, what you did was you changed the concentration of the electrolyte solutions. In B1, you were going to change the concentration of copper. So that was an unknown, but everything else in the Nernst equation is known, so you can calculate the new concentration of copper. In part B2 in the lab, the unknown concentration was going to be the electrolyte silver plus, and that's going to be the unknown. But you can apply the Nernst equation in neither case and calculate concentrations. But the Nernst equation is derived from the change of Gibbs free energy under non-standard conditions. Remember, we derived this equation in thermo. Well, now that we have our relationship with delta G, we could just make those substitutions. And then after we substitute that, we can clean it up a little bit and take a look at it in this form. And this is the form that's called the Nernst equation, where non-standard cell potentials are related to standard cell potentials plus this correction for non-standard right here, where uh, is the ideal gas law constant in units of 8.314 joules per mole K. T is the temperature in Kelvin. N is the number of moles of electrons transferred. And F, of course, is the Faraday constant. And Q, well, Q, we know that's the reaction quotient. And we use that in equilibrium mostly. Now, in lab, you use a somewhat more simple case for this for situations where you're not going to be changing the temperature. So the temperature is a constant, and we use room temperature to approximate that for your lab. And this is often done, so a somewhat simplified version of the Nernst equation is often used here, where all of these constants are collapsed. These guys right here, RT over F. And there's a factor of 2.3 for the conversion of the natural log to log, log base 10. So when you do that, you collapse all those constants, and that conversion from natural log to log base 10, you get this number right here, this 0.0592. And that's what's often used, and that's what you're going to use in lab. All right, we were talking about concentration cells and how the Nernst equation can be used for concentration cells. If I have a cell that's exactly the same as another cell, and maybe you guys can do this because it's good practice, and that is just try to build two exact cells made of nickel. One half cell here, another here, salt bridge, nickel plate, um, I have a nickel 2 plus here, nickel 2 plus, some salt, voltmeter, nickel electrode here and here. Can anybody tell me what the voltmeter reading for this situation would be? Now they're two exactly the same cells on either side. So what's the potential difference?
I
Zero?
Change the
Zero,
concentration.
yeah. So E cell would be 0 for this, right?
I was gonna ask about concentrations, or did you say that?
Yeah, no, I did. Yeah, it's the same cells.
Okay.
Okay, but now, and I think you can see that. So E would equal E0 minus 0.09, point oh, what was that value? It's not 0.0592, right? There, I think that's it. Let me just check it real quick. Yeah, 592. Over N times the log of Q. All right. So they're exactly the same. So this guy's going to be 0. So E cell is going to equal the standard, sorry. If it's exactly the same value here on either side, then E cell is going to be 0 for that. Sorry. All right. And now, if they're the same concentrations, then Q is going to be 1/1 or whatever that. So that's going to be 0 too. So E is 0. But now if we have, say, one of them is dilute and one of them is concentrated, then we have a situation where nature is going to want to spontaneously send electrons in that wire to redistribute the concentrated side, because remember, nature tends to spread out electrons. I'm not electrons, particles, and or energy. So it's going to want to make the dilute side more concentrated and the concentrated side more dilute, if it could, by sending electrons through. And so you might guess from second law of thermodynamics that the half cell reaction on the dilute would be one where nickel goes to nickel dilute, so I produce more, plus 2 electrons. And over here on the concentrated side, I would predict the reduction. And so that would continue until those concentrations equal, when the cell voltage would be 0. Let me see something. I'm getting some feedback from somebody's yeah, I think you fixed it. Thank you. All right. So we see that we can have this. No, I'm still getting that feedback. Can someone shut off their speaker? It just happens when I start talking, I think. Okay, I think it's better. Maybe not. I can mute myself. Anybody have any questions so far? Let's see. Yeah, it looks like everybody's off. Let's see, Lindsay. Okay, thanks. All right, so we're good so far with this thing. You agree that nature would tend to want to change those concentrations spontaneously, and it can do that by sending electrons from the dilute side to the more concentrated side. So the concentrated side would get less concentrated and the dilute side would get more concentrated. So if I added up these two half reactions here and here to get the whole reaction, I would have nickel plus nickel 2 plus concentrated goes to nickel 2 plus dilute plus nickel. And so now, once I have this overall redox reaction for the concentration cell, I can define N and Q. So N is going to be the total number of electrons transferred, that's 2. And Q is going to be defined as the concentration of nickel 2 plus dilute, that's a product, over the nickel 2 plus concentrated, which is a reactant. And so when I plug that all in with this situation here where the dilute side is 1 times 10 to the minus fourth, and the concentrated side is 1 molar, I see I get a value of 0.118 volts. So it's kind of interesting. A concentration cell only differs by the concentration of the electrolyte, but everything else is the same, but you can still produce a voltage difference. All right, so that's 2 uses of the Nernst equation that you're going to be able to apply. All right. This talks about what happens at equilibrium and how you can look at the derivation of one form of how K relates to E cell. Then there's a quick discussion of the different types of batteries, dry cell batteries with zinc and a ammonium paste. We have the familiar car battery where lead gets both oxidized and reduced. So in this reduction here, I have lead plus 4 going to lead plus 2. So it gets reduced. On the anode, I have lead 0, oxidation state is 0, goes to plus 2, so it gets oxidized. So each one of these, when I add up the anode and the cathode, the oxidation and the reduction half reactions, I get about a 2-volt difference. And if I put 6 of those in your car battery, I'm going to, in series, I get a 12-volt battery. Fuel cells are interesting to look at because they in the process they use oxygen and hydrogen and they produce water, so it's kind of friendly in that respect. On the other hand, you remember the Hindenburg, well maybe you don't, but anyway, hydrogen is very explosive, and so for a car application, it's probably you're going to have to work out a way to get hydrogen on demand and not store it, because if you get in an accident, you can imagine what happens. All right, this is just a look at what a fuel cell might look like. We have some porous carbon electrodes in here. In lab, you'll be using your carbon electrode, which is the one that you call the graphite. And the reason why you need that, and the reason why you need it in this application, is because the redox reactions don't have an active electrode. They don't have a solid surface allowing for the exchange of electrons because they're gases. Oxygen's a gas, hydrogen's a gas. So you have to supply an inert electrode, and carbon is really good, or graphite, and it's reasonably priced, unlike platinum in your car with the catalytic converter. All right. This leads to the last kind of big topic that we discuss in electrochemistry, and that's the direct redox reaction, like you would find in the corrosion of iron. So we know that the reduction potential of iron is less than the reduction potential of oxygen. So oxygen is preferentially reduced by iron, and that leads to rust. And a nice way to look at this is this picture here. So iron, that surface, acts as both the anode and the cathode. It supplies the solid surface for exchange of electrons. So I have this iron surface, uh, and it comes in contact with water. So water falls on it, and it allows oxygen to, in the water, to take the electrons from the iron, the Fe here, and it goes into solution as Fe2 plus. It leaves the electrons behind, and the oxygen can get in there and cause this iron oxide or rust. And then, as you know, this rust flakes away, exposing new iron, and it just keeps eating your iron away until something fails. So what can you do about it? After studying it and understanding what's going on, someone came up with the idea of sacrificial anodes. So I see that zinc uh, has a lower reduction potential than iron. So that means it's preferentially oxidized over iron. Remember, if we wanted to change these into oxidation potentials, we would have to change the sign. And we're talking about now oxidation of zinc versus the oxidation of iron. So EOX for the zinc is going to be 0.76, and the oxidation potential for iron is going to be 0.44. So zinc is higher up on this oxidation rating. So it's preferentially oxidized over the iron. And that's what happens when you coat iron with zinc. And we call that galvanized steel, when it has a coating of zinc on it. So check out how this works. So we have the zinc in contact with the iron, and electrons can flow through the zinc and the iron. But when the water droplet falls on the zinc, it more easily gives up its electrons here than iron. And so it supplies the electrons, it saves the iron, and we get a zinc oxide coating. Now, you might say, okay, well, that's going to wear away your zinc, and then eventually you're going to be stuck with the same problem. But that's not quite true, because this further gets oxidized to zinc hydroxide, and then with the CO2 in the atmosphere, this reacts to form a very hard zinc carbonate, uh, like armor or crust. You've probably seen this white powdery stuff on aluminum does it as well. Zinc does it, but this stuff doesn't flake off like the iron does and expose fresh metal. It coats it and protects it. Another sacrificial anode that was sometimes used, it's not used as much anymore, is magnesium. And again, it's preferentially oxidized over the oxidation of iron. All right. Now, as always, if you have any questions, just holler. Electrolysis, we mentioned before, and now briefly we're going to go through electrolysis. Electrolysis is when you run non-spontaneous reactions. So for these reactions, the delta G is going to be positive. But what we're going to do is we're going to force the reaction to take place by using more energy than we could have extracted from the natural process. And we talked a little bit about that before. And so that kind of explains the idea of electrolysis. Now, we're not going to change any of our definitions. So reduction still occurs at the cathode, oxidation still occurs at the anode. It's just now that what we're defining as the anode and the cathode, that changes. So remember, we define the signs of the cathode and the anode, and the electrons spontaneously went from the negative anode to the cathode. But now in a electrolysis cell, we're going to force those electrons to go against the natural flow. So we're going to force them to the negative cathode. And that's where reduction is going to take place. But the cathode's now defined as negative because we're forcing the electrons there, and we're forcing this reduction with a higher potential or a larger, a battery with a larger potential. And so we can see how that works in a second or two in a picture. But during electrolysis, we have to watch out, and oftentimes we can't do electrolysis in aqueous solutions because of the possible oxidations and reductions that can happen in water. So we have to make sure that the thing that we want oxidized has a higher oxidation potential than the hydroxide in water, or we can't use it. Or we have to make sure that the thing that we want to reduce has a higher reduction potential than the reduction potential of water to form hydrogen gas and hydroxide. So we have to watch out for these potentials. If not, then we can't do it in aqueous solution, and that's oftentimes the case. So what's done is we just take a salt, for example, and just heat it up until it melts, and it allows the ions to flow in that crystal lattice in the molten state, but we don't have to introduce water. So here's the setup for making sodium metal from sodium chloride. It's a salt, so we can't have any water in there. So we just melt that sodium chloride, the table salt. We heat it up, and you know that these guys have very strong crystal lattice energies. So it's going to take a lot of heat to melt it. But then once it's melted, we can force the flow of electrons using a battery that pumps the electrons from the positive anode over to the negative cathode in this case. And sodium comes up to here and plates out a sodium metal. That's what we want. And the chloride gives up its electrons to form chlorine gas on the plate. Now, I just added in just one of the waters here and to show that the reduction potential of water is higher. See, this is minus 0.83 is higher up on that reduction chart, or is a larger number if you want to look at it, than negative 2.71. So you can't have water around, or this will be preferentially reduced. And the oxidation potential is the same. The oxidation potential, if we look back, is higher than this guy. And so that would be a problem. All right, you can have electroplating. So here we have a picture of nickel plate over here that's dissolving nickel. We're pumping electrons to this other plate here, and the nickel's plating out on it. So we can put anything over here. You can put your baby booties or whatever you want to plate nickel out on, and that's the way electroplating works. Now, in the next few slides, we're going to take a look at some of the quantitative aspects of electrochemistry. So we're often asked, how much, or, what's the voltage that I need, or how long do I need this process to go to give me a certain amount of electroplating. So these problems are no harder than any of the problems that you faced in Chem 200. You just have to keep your units straight. So let's take a look at this first problem. And I have it here in this Word file. So it wants to know, given this reduction of copper, what's the mass of copper that can be produced in 1 hour by the electroplating of molten copper sulfate if the current is 10 amps. Well, the first thing you have to identify is the reaction that's taking place, and they gave it to you. So we have this balanced reaction where we see that it takes 1 mole of, it takes 2 moles of electrons here to form 1 mole of solid copper. So we know our 2-to-1 ratio. We also know that amps is a unit of current, and it has subunits of coulombs per second. So electrons have a charge, and the charge unit is coulombs, and that's related to the charge of the electron. And we know from Faraday's constant right here, 96,500, that should be coulombs per mole of electrons. So that's important. So I can convert to moles of electrons, and then I can calculate the moles of copper, and then I can calculate the mass of copper. So I just got to keep all this straight as far as units go. So I usually start with 10.0 amps, which is coulombs per second. And then it says it's going to run for an hour, which is 3,600 seconds. Okay, so now I have coulombs, and I know 96,500 coulombs per mole of electrons. Then I can times that by 2 moles of electrons per 1 mole of copper. And then I can multiply that by 63.546 grams of copper per mole. That's a 3. Okay, let's see, what do I get? I get 11.85 grams. Did anybody else get that? That sounds about right. Any questions on that? No? All right. We talked about the maximum work and how it relates to delta G. This plate just shows you how that relationship can be used to derive the relationship between delta G and E cell. And I kind of talked about it when we first started our discussion. So if delta G equals work max, and work is a charge right here, a charge through a potential difference, then I can just use that to relate to delta G. And then it makes that connection with kind of stuff that we talked about previously. Sometimes you'll be asked about power in watts, and you'll have to know what the conversion is for that. Now, a watt is a unit of power, okay? And a watt could be further divided into a joule per second. So it's the energy that's exerted in time. That's what power is. So it has a time aspect associated with it. Now, when the electric company sells you kilowatt hours, it seems like a funky unit that they're using, but if you look at watts, which is joules per second, so I have joules per second, and I times it by some time, right? Then the time cancels, and I get joules. So a kilowatt hour is related to the energy that they sell you. It's the total energy that they sell you, the electric company, every month and that you pay for. So you can use the units. A kilowatt is 1,000 watts times hours. So you just, get rid of the hours, use seconds, and then your relationship between watts and seconds and joules. So you see that 1 kilowatt, 1 kilowatt hour equals 3.6 million joules. Okay. All right. So the last thing we want to look at is maybe some problems involving some of the things we just introduced. For example, how much charge is required to produce 1 kilogram of magnesium from molten magnesium chloride? Now, just like we did before, we have to figure that when we melt magnesium chloride, we're freeing up the magnesium 2+ ions. So that's going to take 2 electrons to form solid magnesium. Now we have our relationship between electrons and the magnesium, or we have our relationship between the charge in coulombs and magnesium, because we know Faraday's constant gives that relationship between the charge in coulombs and the moles of electrons. So we want to figure out how much is produced, or how much we need. So I can start out with 1 kilogram, or 1,000 grams of magnesium. And I know 24.3 grams for 1 mole of magnesium. And I know that for 1 mole of magnesium, I'm going to need 2 moles of electrons because of this balanced equation. So that gives me moles of electrons, but they want charge. And I assume that most of the time when we talk about charge, we want coulombs. So we're going to need Faraday's constant. All right. 1,000.3 times 2. Oh, wow, I get a big number. This is 7.9 times 10. 1, 2, 3, 4, 5, 6. All right. The next question, if the applied voltage is 5 volts, how much energy is required in kilowatt hours? So we have to remember that our energy, joules, is a charge through a potential difference. So I need to take that charge and multiply it by 5, and that'll give me joules. So it's 7.9 times 10 to the 6 coulombs times 5 volts. And that'll give me my answer in joules. So let's do that. It's 3.97 times 10 to the 7 joules. And I know that it's 3.6 times 10 to the 6 joules per kilowatt hour. So that's about 11.0 kilowatt hours. Any questions on that?
Nope.
Okay, good. This is kind of like the last bit of electrochemistry where you do the quantitative aspects, and I just wanted to go through a few of these so you didn't think they were you got blindsided, but it's more of the same stuff that you did in Chem 200. You just have to keep track of your units and add in a few more definitions, like Faraday's constant, like the amp is a coulomb per second. and like the kilowatt hour is related to joules. So you have a few more conversion factors that you're used to, but that's about it. Now this next one is about efficiency. Sometimes things will lose more or less energy than other things, but every process loses energy. There's no process that's 100% efficient. So you might be asked, these type of questions, but these questions, I think you could figure out if you just take your time. Like if you were asked, what if it's 63.5% efficient? You can say, well, geez, how much energy would I need in a simpler case, like 50%? All right. So here's how much energy the process needs, right? It needs 11. But if you're only 50% efficient, then how much energy do you have to pump in to do the job? You need 11, but you're only 50% efficient. So how much
Twice as much.
Yeah, twice as much. So you can see that one very easily. Now the 63.5 is not as easy. So you can try to think of an equation that you might derive that works for something and then use it for the one that you don't know. For example, here's the energy uh, in. That's going to have to be multiplied by some scaling factor to give me the energy required, right? So I know that if I required 11, then I have to pump in twice as much, or 22, which means I take the 50% efficiency and multiply it by the fractional efficiency. So now I have my equation. E in times the fractional efficiency equals E required, right? So now I can apply that in this situation, and I just do E in times 0.635 equals 11.0. So for this case, E is going to be 11 divided by 0.635, 17.3 kilowatt hours. So any questions on that? And then the last one, you just multiply by whatever they're charging you and you get that value. So I'm not going to bother doing that one. And this last one I'm going to let you do too, because I have the answer down here and the steps of how you should think about this. So when you read this problem, think about how to solve it. If you need a hint, then turn this upside down and look at it, and then go back and do it again. Now this centers around the definition of the amp. Remember, that's a coulomb per second, and it says if this is a 1.5 amp battery, so that tells you how much charge is moving in it, and we got this mass of lead that's going to get oxidized. How long will that last until you're out of lead? So we need to find the total amount of charge that's going to come from this amp thing. And then once we find the total amount of charge that is required to melt away and use all of the lead, we can use the amps to find the time by dividing coulombs per second into the total coulombs needed to melt that away, and that'll give you your time. And so that kind of it kind of guides you through that here in these steps. And that's it. Any questions? No questions on anything?
Nope.
Yeah, it looks like we're done. So we
Thank
finished.
you very much.
And homework for this unit is on Sunday.
Yeah, I believe it is, isn't it? I'll have to check the schedule.
Yeah, it is.
Yeah.
Yeah, so have you had a chance to look at it?
I'm starting it this afternoon.
Okay. Do you guys want to take a look at it with the remaining time that we have?
Yes, please.
All right.
Yeah. Yeah.
Okay. All righty. There we go. So given the following reaction in acidic medium, answer the following question, the coefficient for water. So how are you going to answer this one? Anybody having any ideas?
Could you just add water in there and then rebalance it out?
Yeah, you could, but I would advise against that because not only do you have to make sure that there's the right number of atoms of the right type on either side of the arrow, what else do you have to make sure of?
So you gotta,
Charges?
Yeah, the
make
charges.
sure
So
that
how do
the
we
left
do that? How do we balance a redox reaction?
half reactions.
Yeah. So this is a redox reaction practice problem. So you got to go back to the steps for balancing redox reactions. First thing I'd do is I would take my time and I would assign oxidation states for everything. I would identify the reactant that gets reduced and the reactant that gets oxidized. I would separate that into their half reactions, oxidation reduction, and then I would just follow those steps that we looked at. Like number one, balance all non-oxygen hydrogens. Two, then go on to balancing the oxygen with water, hydrogen with acid. And then balance the charge, and then add them up, and then cross out anything that's on either side and check the charges and the balancing. So you'll probably have a lot of these, I guess. Okay. So for number two, you're going to have to apply those definitions of oxidation and reduction. Any questions on one or two? Three, again, you're going to have to balance using the half reaction method, and that'll help you identify the lowest common denominator for the electrons that are lost and electrons that are gained. Any questions on 3? Okay, so you're going to get lots of practice balancing. And we did the one of the permanganate with the oxalate. It says when, number 4, when the equation, okay, this is the first basic solution that you have to do it in. Okay, what should you do when balancing a redox reaction in basic solution? Does anyone remember?
You want to add water?
Well, we're going to do that in any case, but the approach for this is to balance it as though it was under acidic conditions, and then make the conversion to basic conditions by adding hydroxide to whatever side has the H plus on. And you got to add it, that number to both sides, then add them up, convert it to water, like you said, and then cancel out any extra water. So yeah, I guess that's what you were referring to. But we did that. So you're going to go back in your notes probably and go over those, and then you're going to apply it to this problem. But there's also a curveball in this one too. They have, let me see, chlorine goes to these, let me get a new guy here. Okay. For this guy, they have Cl2 goes to Cl minus plus ClO3 minus. So when you get these, the first thing that you normally do is you assign oxidation states to see what gets reduced and what gets oxidized, so you can split them up into your half reactions. But you only have one reactant. What are you going to do in this case?
You can do Cl2 twice.
Yeah. Okay, good. So I just wanted to point that out. And so I'm assigning oxidation states here. So oxygen's -2, that's 6. It already got one, so this has to be +5. So now you can see that chlorine gets both oxidized and reduced. So you have to, split them up into your oxidation reduction half reactions. But like you said, you're going to use chlorine twice. One is going to give you the reduced product, and the other one is going to give you the oxidized product. And then it's pretty much the same after that, and add them up. Okay, any questions on that? Oh, and you got to do it in basic solution. So again, you're going to do it in acidic solution, and then you're going to make that conversion. Number 5, when the equation for the following reaction in basic solution is balanced, what's the sum of the coefficients? Okay, again, you're going to go ahead and split that up. This time looks like you're going to have 2 MnO4s in each one. Oh, actually, no. Well, yeah. Yep. So this is similar, but you're going to be using the product twice. And you're going to have to make that conversion again too. So do it in acidic conditions and then convert. Any questions on that? Okay. Again, half reaction method. Same. Same. So you're going to get lots of balancing practice. All right. Now for this redox reaction, they give you the redox reaction. Which of the following are the correct half cells? So they want you to identify what's getting oxidized, what's getting reduced. Any questions on that? So I guess being able to assign oxidation states is going to be crucial for getting that problem. What's the oxidation state? Assigning oxidation states here. Any questions on 10? So the approach for this, if you look at the rules for assigning oxidation states, what are halogens almost always? What's their oxidation state?
+1.
Oh, close. -1. They're non-metal, so they gain electrons. So you assign that -1, and from that you can figure out what mercury is. And if you're not sure about that, yeah, by all means, go back and look at those rules for assigning oxidation states. You guys just need practice, that's all. How many electrons are transferred in the following reaction? You're going to have to balance that. All right. They want you to consider this galvanic cell. They want you to calculate the voltage of the standard cell. You don't have to balance this. It looks like, that they're telling you in acidic solution, but who cares? You don't need to balance this to calculate the cell voltage, right? You just need to look up the reduction potentials and see what their potential difference is, and that's going to be your voltmeter reading. But you got to make sure that you assign it properly. In other words, iron here goes from +2 to +3, so it's getting oxidized. So that's going to hopefully be above, I'm sorry, below on the reduction chart, the thing here that's getting reduced. So I have an oxidation state for chromium here of +6, and it goes to +3, so that gets reduced. So this better have a higher reduction potential than iron 2 plus, or if not, then it's going to come out negative. And it's not going to be spontaneous. And so this, you don't have to balance this equation. You might be tempted to after balancing all those other ones. But here you just need to identify the thing that they think is going to get oxidized, the thing they think is going to get reduced, look up their reduction potentials, and then the thing they think is going to get reduced, you have to take that value and subtract the other. And that's where those equations are handy for calculating cell potentials. In other words, those equations you remember like this: E cell equals E reduction at the cathode minus E reduction at the anode. So you have to look at what they give you and define what the anode and the cathode's going to be. And so it looks like iron's getting oxidized, so it's going to be E reduction of iron 3 plus. You're going to look that up in the table. And the thing that's getting reduced is the chromate. So you're going to have to look that up as well. Any questions on that? Okay. Which energy conversion shown below takes place in a galvanic cell? Yeah, you could probably figure that out if you think about it. Any questions on 13? So the definition of a galvanic cell is a spontaneous flow of electrons. Which of the following reactions is possible at the anode of a galvanic cell? So you need to know what the definition of anode is and apply it. If you have any questions, just holler. I'm just going to go through these as many as I can in the next 10 minutes. Which of the following is true for the cells shown here? Yeah, you're going to apply a whole bunch of definitions here. They talk about the cathode and the anode, electrons flowing in a cell, what's getting oxidized and reduced. And this, is, of course, is the abbreviated cell notation. So you need to apply the definitions for that abbreviated cell notation. So this is the anode solution, cathode solution, and cathode at the end here. So there's a whole bunch of definitions you're going to look at in 15. The anode in a voltaic cell and in an electrolytic cell is, all right, you're going to be comparing those two. We talked about that today.
I had trouble on 20. So there.
You have a question on 20?
I mean, I put an answer, but I'm not really sure why.
Okay, so let's take a look at it. Which metal, aluminum or nickel, could reduce zinc 2 plus to zinc if placed in zinc 2 plus solution? Okay, so to answer question 20, you have to be familiar with the that potential table for reduction. So we've tabulated these tables, and they're all the cell potentials that are measured and published in the tables in our notes were measured against the standard hydrogen electrodes. So they give a ranking, and that ranking is relative to all the other potentials. So when you put it in a table of reduction potentials, it turns out, and you should know this, it turns out that it's also a ranking according to those who are more likely reduced. The ones with the higher reduction potential are preferentially reduced by ones below it with lower reduction potentials. Okay?
Okay. I did
Does
that
that make
wrong.
Okay, so that makes sense now, right? So you got to look at the table and they give you the values, right? So I'm just looking at these values. I'm not even reading the question. I see this is the highest. And then this is the next highest, and this would be the lowest reduction potential.
Okay. I'll have to go back.
Yeah. So you really want to understand that table, the ins and outs of it. And we looked at it. I tried to neaten it up a little bit, and we talked about it last time to show what they meant by the agent formalism, which gets into, the things in a reduction potential table on the left where the electrons are getting reduced. The opposite is oxidation, and those things are on the right, but it could go either way. It depends on what its partner is. And to calculate the potential difference, you can use one of those equations. And the one that's almost always used in your textbook is the one that just uses reduction potentials for calculating that. All right. So I think 21 is kind of the same, but now they're using that agent formalism. So you're going to have to understand what that means. And simply, it means that a reducing agent itself gets oxidized and forces something else to accept those electrons that it loses. So the best reducing agent is going to be the thing most likely oxidized. So if you look at a reduction table, the things that gets oxidized are on the right side of those half cell reactions. And the best reducing agents are the ones most likely oxidized. They're the ones that are lowest on that chart. So you go through that reasoning and you can figure it out. All right, moving right along, unless there's a question. The 22, consider a galvanic cell shown below. The standard reduction potentials, which of the following statements about the cell is false? So again, you're going to have to know the workings of a cell, the meanings of these half reactions. Notice they're telling you the reduction potentials because the electrons are on the left, and that's where they should be. So these are reduction potentials over here. That one's higher up, so that's more tend to get reduced. This is going to be the guy that spontaneously is going to get oxidized. So this reaction is going to run in reverse for a spontaneous process. And so you're going to get a bunch of more of these, practice of how these voltaic or galvanic or maybe below, they'll even have electrolytic. So the voltaic or galvanic, they're the ones that run spontaneous. So they should have E cell values that are positive because that means delta G is negative. And that's what a galvanic or voltaic cell. If they say it's an electrolytic, then you know that you're going to be supplying a power source that's greater than that natural flow. That potential difference for the natural flow of the electrons. That's the only way you can pump them against the natural flow is with a higher potential. So it looks like you have a bunch of these guys. I don't know if there's any one of those ones you want to look at. We did look at one. Which of the following would be the best oxidizing agent? So they're going to use that agent formalism, like we talked about in our one discussion. You wish to plate out zinc metal. Which metal could you place in the solution to accomplish this? All right, so you want to pick something that will allow a spontaneous direct redox reaction. and you want to assure that zinc gets reduced. So what do I have to look up about zinc, aluminum, and nickel and compare? Does anybody know?
I mean, it looks like the same
Reduction
thing as
potential?
20.
Yes, I heard it in there. You got to look up the reduction potentials because it's a ranking of them, you know, their propensity to be reduced. Whichever's higher up on the chart is going to get reduced by whatever's lower. So you want to be looking for zinc and make sure that it's higher than one of these. If it's not higher than either one, then it won't work. And I think they have that as an option there. All right, any questions on that? All right, moving right along. Which of the following is the best reducing agent? So it itself gets oxidized. So you're looking for something low on the reduction potential chart and on the right, because it has to get oxidized. And when I say on the right, I'm talking about on the right of the half reaction. So it's got to be on the right of the arrow. Okay. What is this? The cell reaction. Okay, so they're telling you this is, again, abbreviated cell notation. So that defines the cathode, the anode, and the electrolyte solutions. And it looks like we have an inert electrode involved here because the bromine's a gas. It doesn't have a solid surface that will supply exchange of electrons. So you have to put in a solid surface that's non-reactive. And platinum or graphite are the usual choices. Consider the following. Which of the reactions below will see spontaneously? Again, you're going to have to be comparing reduction potentials. So this is testing your understanding of those published values in the reduction chart and what they mean and how you can use them to decide which half cell is spontaneously reduced and which half cell contains the oxidation half reaction, and so forth. So I think if you take your time, you'll be able to learn a lot and figure these problems out. Any questions? It looks like we got some more of the same stuff, more definitions. Here we're adding in some delta G and connections with the equilibrium constant. Oh, here we get to the quantitative problems that we just looked at the last part of the electrochemistry. All right, cool. That's all I got for you guys.
Thanks for going through those.
Hey, anytime. And if, like I said, if you have any problems with these problems, let me know. And I'll usually get to them this weekend within a day or so.
Thank you.
Thanks,
Thank you.
Professor.
Thank you.
You got it.